Well, we have to hurry along and begin this talk with potentials. I introduced it by saying that it turns out that potentials and potential energies, if you can use them for certain purposes, simplify electrical and gravitational problems considerably, mostly because energy is not a vector. It's a scalar quantity. For example, if you have two energies, you can just add them and there's no direction involved. Whereas if you have a force, you have to add them vectorially. So that can be a big advantage. Now, the problem is that there are all these definitions and conventions that we have to learn. But I think that, for example, we have some familiarity just with the idea of gravitational potentials. I mean, we don't call it that, but the idea is if you lift something up, you know that you've given it the potential to do some work. That is, it can go down and move something else. So that is a form of energy. We know that, for example, in the gravity potential, things at the same height have the same potential energy. For example, if I want to lift a heavy box and put it on a shelf, the gravity field is acting on the box. And so when I put it up on the shelf, I'm giving the box in the gravity field extra potential energy. So moving it up and down along the field gives it a potential energy. But moving the box sideways on a shelf doesn't take that much force because I'm not really fighting against gravity. So we get the idea that the gravity affects the potential energy if you're moving for or against it. Whereas if you're moving sideways, it has the same potential energy. I mean, everything at the same height has the same potential energy. In fact, we have a word for that, equipotential. So if you have gravity, the lines of the gravity force are this way, but the potential energy surfaces are this way. That's a force. Let me put down V. V is the symbol for potential. And this will be a characteristic of potentials. This is an equipotential in the gravity field. And there are a series of equipotentials. Now, this could be the top shelf. This could be a different shelf. That's another equipotential. And we would say that this level has a higher potential than this level, right? I mean, it's just higher shelf. And we've lifted it higher. So actually, the field has done more work, negative work, actually, to get it up here. I have to say that we struggle with the idea of who's doing the work. I think I mentioned that earlier. And different, very great experts in the field differ on what they talk. In fact, in your book, Wolfson switches between whether you're doing the work or the field is doing the work. It's a funny thing, but different experts look at it differently. So, for example, in this case, let's say I have a box, and I lift the box. I put the force on the box to put it on the shelf. Now, what's the gravity field? This is me. This is I. This is I. It is I. right? Okay, people always get that wrong. Okay, but the gravity field is the force of gravity is that way. So we will take a definition that we're always going to consider what is doing in the field. So I'm going to choose this definition. In other words, if I lift this box upward, the distance that it moves is opposite to that of the gravity field. So the gravity field does negative work, is the force of gravity times dx. In this case, those are vectors. Again, force of the work is a scalar, is just a number, but the force of gravity times that distance moved, in this case, will be negative because the gravity is this way and the force is that way. So we would say that the field has done negative work. Whereas if the box falls off the shelf, the gravity field and the direction that it's moving are in the same direction. So if the box falls off the shelf and it falls a distance dx, and the gravity field is that way, then the work done by the gravity field, you see this is positive because the gravity field, the vector, is parallel to the dx. So this is a positive work. So we get the strange idea is this one, where the field can do negative work. Or in other words, one way of saying it is we're doing work on the field. So it's very tricky, but I like this way of looking at things because it takes the anthropomorphic feature out of it. It's not that I am doing work. Think just about what the field is undergoing. So we will just stick to this approach, namely, don't worry about what I'm doing, just worry about what's happening to the field. And then I think things work out very nicely. So, and then what we have shown is that the work done is equal to, here's where the negative signs get kind of funny, the change in the potential energy, but with a minus sign here. And you'll see how that, sticking to this kind of definition, you get the law of conservation of energy comes out because the work done is equal to the change in the kinetic energy. This again is the analogy of the bobsledders. If he does work, in other words, the bobsledder gets, the guy who's pushes the sled, puts a certain amount of force through a certain amount of distance, which is the work, and he ends up changing the kinetic energy. But look what happens if we define it this way very nicely. If these two are equal, K final minus K initial is equal to minus U final minus U initial, with that minus sign. Let me put all the final things on this, final things on one side, initial things on the other. Okay, so I get minus K initial. The U initial is plus, minus and minus makes a plus. I bring it over here, minus U initial equals, and I put K final on the other side here, minus K final, and I have here minus U final. Well, I got a lot of minuses sign. I'll just multiply through by minus, and I get the law of conservation of energy in a potential field. That is that K initial plus U initial equals K final plus U final. See, by choosing the sign that way, I get this nice statement of the conservation of energy. That is to say, the sum of the kinetic plus the potential energies is a constant in the field, which is what I'm saying here. If I raise this, I give it some potential energy. If I drop it, I lose potential energy, but I've gained kinetic energy while it's falling. So that's a very powerful law. And we just have to be a little admiring of the fact that people figured this out, and so you sort of keep it in your head, where do you put the minus signs? You got to get used to this. It's really not easy. So we have this familiar example of gravity. We do it not knowingly, but we do it all the time. Lift things up and see them fall. First thing a child does is pick things up and throw them on the floor. So now the similar thing is true with the electrical field. Both of them are conservative fields. They both have this fact that they have a potential energy. The fact is that the electric field, for example, we've come across electric fields of the same type as this, where, for example, you can, to make a field or a force, well, to do the electrical case, there's a little difference, because here we have a choice of charge. The case of gravity is always attractive. Here's the Earth, and here's an object. The force is always attractive. Now, with electric things, we have the option of two different charges. But, okay, let's pick the plus charge for the sake of argument. In which case, you know, the field is, for a plane, like, then we define the electric field as running away from plus charges. So we have here, but if this is a plane of charge, then again, we have a uniform electric field. Again, this is a symmetry property. If you have an infinite plane, there's no reason why the line should point to the right, the left, forward, or back, so they will point vertically upward. Moreover, if it's an infinite plane and there's no other negative charges there, these lines can't end. So you have the case of a uniform field in the case of a plus charge like this. This can also be proved by using Gauss's law, that in the case of an infinite plane. In other words, this is a similar situation, except for the direction of the electric field compared to the gravity field. But here, the electric field is this way. But it's a similar case, and we can define similar things. We can define the potentials in here. In other words, if I'm a plus charge, well, that wouldn't be, yeah. If I'm a plus charge, now here's where the sign difference comes in and complicates things. If I'm a plus charge, I'm repelled by this plate here. So it's opposite to the gravity field. See, the force is now this way, whereas the gravity force was downward. We sort of reverse the story. It would take work to push work by the field. The field is going to do negative work. If I push that electric charge downward toward this plate, the force is that way, the direction is that way. If I push a positive charge down, then my f dot dx, being in opposite directions, will be negative. I'll do negative work. Work is negative. But the change in potential, being the opposite sign, is positive. So I increase my potential by bringing the plus charge toward the plate. That makes sense? The fact is, you see, it doesn't want to be near the plate. But if I push it down, I increase the potential because it wants to spring back. So I've increased the potential of its moving. Whereas if I take it further away, it's used up some of its potential because that's the way the field wants it to go. That's the kind of feeling I want you to have of this property. Now, So this is a definition of potential, and here is actually sort of the mathematics of it. It's a little unfortunate that it's a little bit mathematical, but it says what I just said here. Namely, that first we define what we call work, which is a force acting through a distance. And I showed you, I think last time, that if you have work done, it will produce change in kinetic energy, all things if those are the only things acting. And in this line here, I define the change in potential from final to initial with a negative sign compared to the work that is done. Now, the work that's done by the field is this Q0, the force is Q times E. And the work done is that force, QE, times the distance through which it moves. So that is the change in the potential, what's called the potential energy. That's an energy because work and energy are the same thing. That's what this line means. Now, the other concept that we have is that of we have the one idea is potential energy, which is, it's an energy, it's in units of joules, or joules, I guess, is better. Joules sounds kind of jowly. So that's an energy, and it's a force times a distance, or it's a half mv squared units of joules. Now, just as we can actually look at the units here are, it was force times distance as a unit here. The force is given by QE, right? Electric force times dx. Now, we can get another quantity of interest by dividing out the Q. So we get du per Q, and that is equal to E dx. So this quantity, that is the energy per charge, is called the voltage. The analogy here is to when we first defined the action of two charges on each other. We started out saying that first there was a force between them, which was related to Q1 and Q2 over r squared with some proportionality constant. But then we said, no, let's look at it a little bit differently. Let's imagine Q1 here is producing some influence in the field. This is the force of 1 on 2. Let me just figure out what does the field do to 1. Charge 1 is creating this field out here. And the way we got that, we took the force of 1 and 2 and we divided by Q2. So we got K Q1 over r squared. So we were trying to say this is an influence due to 1, and then we can put Q2 in that influence, but this is kind of like a free-floating thing that's just there, created by Q1, but we just put Q2 in there, or Q3 or Q4, but whatever it is, Q1 has produced its thing. It's only dependent on Q1 and the distance, and you can put the Q2 any place. So we're doing a similar thing here. We're going to define, we have defined the energy as something Q times E, but you see E was produced by somebody else. See, I put this Q in an E field, and I multiply by dx. I can get the per unit energy by dividing through by Q. So I get something which is analogous to this quantity here, something per unit charge. It's the energy per unit charge, which is volts in units is joules per coulomb. But that the unit volt is used so much that the joules per coulomb is used so much that we give it its own special name, volt. And your batteries come with both ones. You get a 1.5 volt battery, you get a 9 volt battery. In your car, there's a 12 volt battery. It's the energy that any charge coming out of your battery, each unit of charge will have an energy of 12 joules per each coulomb. So we'll get used to that notion pretty soon. Now, there's a lot of stuff here. The only thing that I would do now quickly, if I can, is to find the potential due to a particular charge. As I say, the potential V is just due to the electric field due to some charges times some distance, and you can get the voltage, the shelves that it's built on. So now here's one case, the planar situation. The opposite of that, in a way, is a point. See, this is an infinite sheet. Now you can find the potential due to a point charge, just Q. We know it has electric field going out now like this. Now, similarly, what we're going to do that thing here. We're going to find the voltage or the potential at some position R by doing that integral, the integral of E times dx between 2 points. So what voltage gives you is the energy difference. Just like if I put something on a shelf over here, it has a certain potential difference between here and the table. There's a difference between this level, height 1, height 2. But on the other hand, that same level with respect to the floor has a different potential, because this thing will be moving faster when it hits the floor than it hits the table. So we always measure with respect to a difference when it comes to potential energies, because there is no absolute value. How much potential energy does this have? Well, depends where I am. If I'm on the 3rd floor, I have a certain potential energy with respect to the 3rd floor. On the other hand, it's a different potential energy with respect to the 2nd floor. And with respect to the 1st floor, it has a different potential energy compared to the top of the campanile. So there's always a difference. So you integrate between 2 points, x1 and x2, and you get a difference. And this will give you V2 minus V1. So that's the gist of this derivation, which is in the book. So maybe I shouldn't go through it. If you don't like integrals, this may appall you. But it's a relatively simple integral, because you're putting in here the electric field. And the electric field we know is 1 over 4 pi epsilon naught Q over R squared times, what we're doing is we're going to integrate, what does he do, from R to infinity. So he's going to start at R, and he's going to integrate how much force, or how much is the field as I integrate all the way out. Now the field is changing. E is Q, this Q here, maybe make it big Q, over 4 pi epsilon naught r squared. So as I go out, this field, E, is changing, and I multiply it by the element of distance I go through. This force, the field force is acting through that distance, and I keep adding up all those fields and distances from r all the way to infinity. That's what that integral is trying to tell you. And because this is a known integral, you know, the integral of r squared, 1 over r, we'll think of it as r to the minus 2 dr, for those of you who like math. It's equal to r to the minus 1 with a minus sign, integrated between r and infinity. So that's all they're doing there, and you get a 1 over r dependence, that you get that the voltage, the potential at a point r is just q, the same q that started it all, over 1/4 pi epsilon naught, but it's now inversely as the distance. And the nice part also is that it's a scalar. So you can, if you have two charges, q, they make this q1, q2, if q2 has a certain potential at that point, and this one has a potential at that point, you just add them up, and you got your answer, total potential. And it turns out to be nice. And then again, I repeat this yet again, why potential energies are useful is because, again, they are conserved. That is, total kinetic and potential energy starting will be the same when it ends. Yes, ma'am.
On the previous slide,
Yes.
why on the very last line of the equation do they go back to using the lowercase r and not the uppercase r of the line above?
That is probably my fault, because I cribbed these equations from two different places, and people use big R, and some of the people use little r. But what it means is the point that you're integrating to. In other words, you start here and you integrate to infinity. You want to call it r or little r, it's the same. It's just that, yeah, that's a good point. Sorry if it confuses you.
They have both the little case r and the bigger
Yeah.
r, so can you just clarify the difference?
Oh, yeah, well, one is a variable. In the integral, it's a variable. See, no, see, that's my fault. This should be a variable. It should be the same variable as this. And this is the place I'm starting, and this is the place I'm ending. And this is r, little r is a variable. It should have been consistent, sorry. No, you're right. Should have been 1 over r squared, the variable, and I integrate the variable, and r is the limits that I'm integrating between. Yes, you're right. And in fact, the big equation v here, it should be the v at the place I'm interested in, big R probably. Good point. I'll have to modify that slide. Thank you. Did you see her point? Her point was which are variables and which is a constant. All I'm doing is trying to go from one place in the field, like from big R, out to infinity. And I should have made the notation consistent. Okay. Good. Now, going back to this. Now, I did give you that sample problem of the stopping. Do I have time? No, I think I would, let me take 3 minutes to just sketch out a slightly different problem to show you how you can do some pretty nifty things. The stopping problem, we almost finished it. Oh, well, let me see. Talking about, well, let me do one more slide here. This is the graph of the potential of a point charge. Because the point charge, the potential of it is 4 pi q over 4 pi epsilon naught, or, you know, we could have put k, 1 over r. What it does, if it's a positive charge, it just goes up like this. but it's true in every direction. So you have V, and this is proportional to 1 over R as you go out in R. So that's what it looks like, which means we're assuming here a positive charge source, which means that if I'm a positive charge, as I get closer, my potential increases if it's a positive charge, which is right. In other words, it's a positive charge gets closer to another positive charge. It wants to get away more and more, and if you let it go, it's going to release. So the potential gets higher as you get closer. And it's also true, it doesn't matter which direction you come at it. If it's a point, you come at it this way, and you're rising the potential. You come at it this way, you'll be rising. Come at it that way, you're rising, right? It's because it's spherically symmetric. So that's what that diagram is supposed to show, that these potential surfaces, no matter which way you come at it, it's kind of a tower or pyramid-like, but it's 1 over R type dependence. Well, what I wanted to show you very quickly, let me just write down the results. Now, I will put this into on B-Space. I don't have it in my notes, but I wanted to show you even a harder problem than I started out with. Remember the problem I started out with was 2-point charges, 2 electrons, say? It's noisy. Separated by a distance d. And I would start it out with another electron way out here at infinity, and I wanted to know how would I shoot this electron and have it stop dead in the middle of those two. And we pointed out that if you try to do it by forces and fields, it's a lot harder than if you try to do it by energy and potentials. That was the gist of this thing. Now, what I want to show you now, let me make it even stranger than this. Let me make a ring of charge with this amount of Q on this ring, a thin ring. And I'm going to do the same game. I want to start out and make it a negative charge and maybe an electron over here. And I want to say I'm going to shoot that electron with some speed I don't know. But what I want it to do is to arrive here and stop. And the reason it'll stop is because the electric field is opposing its motion, right? Because this is negative, so the electric, here, let me plot this very interestingly, I think. Let's plot the electric field due to this. I did this actually once before with you. The electric field as a function of distance along the axis. I think we did this in class. If this is a ring of charge, uniform, what's the electric field at the center? 0, right. Why? Because for every charge here, these are negative, so they're going in. For every one going in, there's a charge on the opposite side. It's symmetrically opposed going in the other way, so it's 0. Then we asked, suppose you go very, very far away. What does this look like? Point charge of charge Q. So way out here, it's going to look like that. So the electric field, but the electric field is inward. So I don't know how to represent that exactly. Maybe I'll make it negative, like this. And it must pass through 0. And it's negative because it's pointing inward in a way, you know, or I could draw it maybe this way. Let me get some colored chalk, maybe like this. It's a little weak here. It's stronger here, stronger here, strongest at some point here, and then it must get weaker, weaker, and be 0 here. Yes, sir? It's not a point charge, but when I reach the center, it's got to go to 0. So the electric field, in other words, if here's the ring, as I'm approaching it, I feel the electric field. The other thing I'm going to plot, though, is the force. So you got to be careful here. The force is equal to Q times the electric field. Now, Q is, in this case, is negative. See, I made the ring negative, so that's why I'm making the field negative. But the force is Q times E. Q is a constant, but it has the same sign as E, so it's going to be positive. So the force is going to look like this. I'm in trouble. Or do I need another color? So these are the kinds of things you just want to have a little feeling for. The force will go up, and because the field reaches a peak, the force will reach a peak, and the force will go down to 0. So this is the force. And the force is, in a sense, positive. It's pushing the charge away, right? Because it's a negative ring. It's a negative charge coming toward it. The force will be opposite, but the fields will be officially the fields are negative, right? Because they're going inward. So that's the way that looks. And it's actually interesting. If the thing overshoots, the field will reverse, because it'll pass. Things are continuous. And in fact, the field will start to go that way, right? Because it's pointing toward the charge. And the force will also reverse sign. Okay, now just for fun, let's see, and I want you to get a feeling the difference between the forces and the fields and the energy. If you have the ring like this, it will turn out that see, I have it worked out. It's in the book, actually. This by the way, the quantitative answer is given in Wolfson. Example, not a, yeah, 20.6, page on 341, where he gives you the exact formula, which looks like that. Then he also works out, when we come to the section on potential, he works out on, this is now Wolfson, example 22.6 on page 379, where you find that the potential along this axis is given by KQ over the square root of x squared plus a squared. Now let's look at the difference between what the potential is doing let's do the potential as a function of distance, and let's do the potential energy as a function of distance. Well, let's just, without even looking at the formula, here you have a negative charge. Negative charges, if you have to think for potential, you have to think per unit charge. So a negative charge a positive charge would like to go here. See, when you're thinking of potential, it's per unit plus charge. So the potential actually, the potential will get lower and lower as you go to the center. In other words, a plus charge will use up all the attraction. See, a plus charge is being attracted to this ring. So his potential will go down as he gets to the ring. Where did I should have put that in the right place. Here. Potential will be this. This is the V. Now, on the other hand, the U is equal to Q times V. Now, I'm having an electron come in from the distance. That's negative. The V is negative. So what's going to happen is my potential energy, U, will, because I'm minus times a minus, my potential energy will go up. This is U. Pretty strange stuff going on here, huh? The point being that this negative charge is going toward a negative ring. And it's going there because it just has speed. It's inertia. Yes, sir?
If the negative charge is going towards that negative ring, wouldn't the potential be negative if we want to get away? So would the lower potential farther away from the ring and pushes the ring?
That's right. It's a lower potential further away from the ring. Here's the ring. The potential energy is going up. This is the potential where you're assuming here a plus charge. See, when you define the electric field, I defined it was negative here because it's what a positive charge would see. We always define the electric field and the potential as what a positive charge would see. So this is the potential that a positive charge would see. This is the potential energy. So what's happening here is this thing starts out with kinetic energy, a half mv squared way out here, very low potential energy. But as he runs in, he transfers his kinetic energy, and he gets a lot of potential energy as he runs toward the negative charge by inertia. Okay, write this down. I'll put it on the internet. Oh dear, we have just 5 minutes. Or less. I want you to be able to distinguish between a field, a force, a potential, and a potential energy. These are important ideas. They're a little tricky. But let me kill this and put this guy away. I wanted to give you a quick touch of dear me. Electric circuits. There's a little spiel here. We're into a different thing. We're into the lower part of this diagram now where charges are allowed to move. The difference is, in the first, what we've dealt with up till now, say you had a body like a piece of metal, and you put it in an electric field. It's just a lump, and what will happen, the charges can move within this lump, and it can move from one side to the other, get polarized, but they can't get any further. They can't get off the lump. So what happens in the case of what happens, the charges, originally it's pretty well uniformly distributed around the metal. You put on a field, the positive charges will run that way, the negative charges will run this way. You'll get a field created by these charges, and inside a conductor, we get no field because these charges here are canceling out the field you put on. As we said, inside a conductor, the field is 0. But now we're going to do something else. We're going to have a chunk of metal, but we're going to put on a steady electric field, and we're going to allow the charges to run from the source, from the battery, back into the battery. You always have to have a closed circuit. For example, if you turn on a flashlight, what are you doing? Well, you are, right now it doesn't light no matter what I do. The reason this part is completing the circuit. What it's doing, I hope you copied this down, but I will, as I say, so what this is that you have a lamp and you have your batteries, and what you're trying to do is connect this with this. And there's a little switch in here. That's this guy here. He just goes click and he completes the circuit. Now I can do that with this little thing here. See, here's my battery, and here's the thing that's going to lead back here. And let's see if this works. Did it light? No? Oh, maybe I should switch it on. Yeah, you see, I'm completing the circuit from the thing here to the battery. And then but so you must have a complete circuit. It's kind of odd. You never lose the electrons. The electrons are sort of like a continuous body of water where they have to go back to the source, and then they get pumped up again, and then they come back. In this case, the battery is sort of like a source of charge. It's like a negative charge and a positive charge. The negatives want to run to the positive, and in so doing, you make it run through the wire. So think of it this way. These guys, this is the negative end usually. These negatives want to run to the positive, but in so doing, you make them run through the wire. You make the wire hot, and it glows, and then you have a flashlight. So that's what's happening here. Some folks have told me that I run over, which I have just done. I'm about to do again. That's a break. In any case, very, very simple. I just want to define a couple of very simple things. To have a circuit, you must have a source, which in that case was a battery. You have to have a continuous path, and it passes through some objects, which you're trying to do some work with, like this flashlight. So you define here a couple of very simple things. A current. These are in my notes. The current is a flow of stuff. It's the amount of charge, Q, per second, passing through this wire. It's like the gallons per second flowing through a pipe. Then you have the idea that if you have a split in the line, for example, if you have a path like this, the water that's coming in must go out. So it must split such that I1 is equal to I2 plus I3. It doesn't, you don't lose anything because the charge can't accumulate. They hate each other, so they're going to keep going. And so that's an important point. And the reason the flow goes at all is because there's something pushing. So for example, in a battery, basically you have sort of minus and plus. The charges want to run to the other side. Or, as I say here, there's lots of different ways you can get that push. It's sort of like a pressure difference between two water tanks. If you have a lower water tank, if there's a pressure difference, the water will flow. And the sources of this electrical pressure, also known as an EMF, we have our dry cells. You have the wet cell, like in your car. Your electric power company provides you with a push coming out of the wall. You'll have a power supply in the lab, which between two terminals, you'll get push. Solar voltaics, like in your little computers or calculators. The sunlight comes in and it generates electric charge separation, and the negatives want to run to the positives. Friction, like we did in the Van de Graaff, or lightning. Lightning builds a tremendous pressure of electric pressure between the cloud and the ground, and so much so, like a Van de Graaff, it'll arc across. That's your lightning. And we have other fuel cells and other things like that. So you need something to give you a push. And we measure that as the energy difference voltage between here. You have the wire, which carries the current. And then the other quantity that you have here is called resistance. And that's because we're now trying to pass this electric current through a wire, through a material. Not like, as I said, not like we had before where you had a vacuum and the charge would just go freely with F equals MA and F was EQE. Now you have resistance of the material. Now, for example, if the normal thing, if there's no resistance, the ball falls freely in the gravity field. Here, I'm imagining it's going through a material. And the material is kind of, this is pretty regular stuff. Your typical metallic wire is not so regular as this, but even this pretty regular set of nails will impede the flow. See, and that's a lot slower than this. So you see, that's what happens when you try to push. See, we've created what's a potential difference by height. And there is gravity force trying to make this thing go down, but as it passes through the material, it goes through this random walk and slows down. So it doesn't really accelerate very much. So there's some opposition to flow in a real material, every material. And the analogy with water is a clogged pipe. And depending on how bad the pipe is clogged, you will get different resistance. And in the electrical case, we call it electrical resistance. And we measure that in ohms after a man named Ohm. Ohm. It sounds very Buddhist, doesn't it? Ohm.